A cosmic dynamo spins at the edge of reality. Civilizations could harvest energy from rotating black holes. They are the ultimate power source in the universe. The physics is real. You can turn a destructive singularity into an engine for galactic growth. So what does it take to build a power plant where space and time twist into a whirlpool? And could we ever siphon energy from the void itself? The difference is in the spin. A simple black hole is just a dark sphere, a one-way door. But the universe doesn't usually make things that simple. Most black holes come from a star that was already spinning, and that spin gets preserved. It gets amplified. It gets concentrated into a kind of cosmic whirlpool. Those are called Kerr black holes. Their structure is much stranger. At the center, you still have the singularity, that point of infinite density, but around it, there isn't just one boundary. There are two. The inner one is the event horizon, the point of no return, but outside that, there's a second surface. It's invisible. It's shaped like a flattened sphere. That's the ergosphere, and in that region, the rules start to come apart. Inside the ergosphere, something extraordinary occurs. The black hole's spin drags spacetime itself into a vortex. It's like stirring honey. That effect is called frame dragging. It's so powerful that nothing can stand still, not even light. Everything is forced to move with the spin. But here's the crucial part. You're not past the point of no return yet. The ergosphere is twisted spacetime, but you can still escape, and that creates an opportunity. Because in this zone, the definitions of energy and motion become fluid. Physicists talk about orbits here that have negative energy. It's a bizarre idea. Relative to the distant universe, an object could theoretically lose energy by falling in. And if something can lose energy, then something else has to gain it. This isn't magic, it's rigorous mathematics. It's a loophole in the equations of general relativity, written by the sheer torque of a spinning singularity. So the ergosphere isn't just a zone of distortion. It's a reservoir of power you could extract. It's a dynamo waiting for a wire. To tap it, you wouldn't fight the gravity. You'd learn to surf on the spacetime whirlpool. The blueprint for this cosmic power plant was drawn over half a century ago. Back in 1969, a physicist named Roger Penrose looked at the equations for a spinning black hole. He saw a glimmer of possibility there. He proposed a thought experiment, a precise sequence of events that could turn the ergosphere's twisted physics into a power source. It starts with a simple delivery. You send a probe, or maybe a large container of matter, on a trajectory that takes it skimming into the ergosphere. This object carries a certain amount of energy, measured from the calm, distant universe far from the black hole. Once it crosses into that whirling zone of frame dragging, everything changes. The object is caught in the spacetime current, forced to move with the black hole's rotation. And here, Penrose envisioned a clever maneuver. The object splits in two. This isn't an explosion. It's a precisely engineered division. One fragment gets a carefully calculated push. It's sent on a trajectory that dives down past the event horizon into the black hole forever. The other fragment gets a push in the opposite direction. It aims to climb back out of the ergosphere and escape to safety. The magic is in the accounting. The fragment that falls in does something seemingly impossible. Relative to the distant universe, it carries negative energy. It's as if by falling into the black hole in just the right way, it actually reduces the black hole's total mass and rotational energy. That lost energy doesn't vanish. It has to go somewhere, and it goes into the other fragment, the one that escapes. This escaping piece rockets away. It has more kinetic energy, more raw speed and power than the original whole object ever possessed. Think of it not as creating energy from nothing, but as a cosmic bank heist. The falling fragment is like a thief who jumps into the vault, taking a bag of gold with them. But in doing so, they fling an even larger bag back out to their partner. The black hole's rotational energy is the gold. The escaping fragment is the loot. This is the Penrose process, a direct mathematical conversion of spin into usable power. It proves the energy is there for the taking, a rigorous prediction of Einstein's theory of general relativity, not mere speculation. It was the first concrete blueprint, showing how a civilization could, in principle, harvest energy from a rotating black hole. But a thought experiment is one thing, building the machinery is another. The blueprint needs a workshop, and for the Penrose process, that workshop is a place of pure motion, a cosmic arena where the fabric of reality is in constant flow. That's the Ergosphere. It's not a solid shell. It's not even a surface you can touch. It's a region of influence, a flattened bubble of twisted spacetime that wraps around the black hole's equator. It bulges outward where the spin is fastest. Picture a sphere of dark water, but instead of water, it's space and time. At its equator, the spin is so violent it flings the sphere outward. It creates an oblate shape like a spinning bead of liquid. That distorted zone is the Ergosphere. Its outer boundary is where the drag becomes absolute. You cross that invisible line and you can no longer resist the current. You are caught. Inside, a fundamental rule is broken, the rule of standing still. In the calm of distant space, you can fire your thrusters and come to a halt. You can stop relative to the stars, but within the Ergosphere, that's impossible. The black hole's rotation drags spacetime itself into a vortex. That vortex carries everything with it. It's a cosmic river, and the current is the structure of the universe. You must move with the spin. You are compelled to co-rotate like a leaf in a whirlpool. This relentless motion is not a barrier, it's the source of the power. Because within this forced rotation, the definitions of energy and momentum become fluid. An object's energy depends on who is measuring it. From the perspective of the distant universe, a particle following a very specific, carefully plotted path inside the Ergosphere can be in a state of negative energy. It's as if, by being in that specific place and moving in that specific way dictated by the whirlpool, the particle owes energy to the universe. That's the loophole. That's why the Penrose process works. The Ergosphere provides the unique environment where such bizarre orbits exist. It's the only place in the universe where you can drop an object into a gravity well and have the universe register that act as the black hole losing mass and spin. The escaping fragment carries away the difference, the stolen rotational energy, so the Ergosphere is more than a feature, it's the active component. The dynamo's rotor, the turbine's blade, any practical technology, any design for a power station would have to operate entirely within this zone of chaotic flow. You would need to navigate its boundaries, plot trajectories that serve the spacetime current, position your machinery where the physics allows for the energy transfer. Without the Ergosphere and its extraordinary properties, a spinning black hole would be just another dark pit, but with it, it becomes a beacon of possibility. A whirlpool in the void that could, one distant day, light up the galaxy. The Penrose process is mechanical. It's about throwing things into a whirlpool. A technology of mass and momentum, but nature uses a different currency, a more fundamental one, light and fields. There's another way to tap a black hole spin. A much more powerful way, one that doesn't need probes on a suicide dive. It works on the electromagnetic fabric of the universe. That's the Blandford-Znajek process. It could be the universe's own blueprint for a power plant. To see it, you look at what usually surrounds these engines, an accretion disk, this huge, swirling storm of superheated gas and dust. Spiraling inward at almost light speed, that disk isn't just fuel, it's an ocean of charged particles and tangled magnetic fields. those fields are the key. They're like invisible threads in the chaos. Then there's the ergosphere, that zone of whirling spacetime. As the black hole spins, it drags these magnetic field lines. It twists them, winds them up like a cosmic spring. That twisting creates an enormous voltage, a potential so huge it tears the vacuum of space apart. It generates pairs of electrons and positrons from pure energy, and it accelerates these particles along the black hole's rotational axis. The result isn't a trickle. It's a pair of relativistic jets, colossal beams of raw energy, screaming out from the poles at nearly light speed. They can stretch for millions of light years. Punching through galaxies, we see this in quasars, the most luminous objects we know. A quasar is a supermassive black hole running the Blandford-Znajek process at full throttle. A natural dynamo on an unimaginable scale. So for a technology, an advanced civilization wouldn't create this chaos. They'd harness it. They might build stable structures. Rings or networks of superconducting cables, positioned in the accretion disk or threading the ergosphere. These structures wouldn't fight the magnetic fields. They'd guide them, shape the twisting process like the coils in a gigantic generator. Instead of chaotic jets, they could channel the energy, induce currents. Direct the flow, transform that electromagnetic fury into a steady power stream. It's like placing a turbine not in a river of water, but in a river of twisted spacetime and magnetism. The black hole's spin provides the torque, the magnetic fields are the transmission, the technology provides the outlet. This method has advantages, it's cleaner. No need to constantly sacrifice matter, it's more scalable, tied directly to the black hole's rotational energy, and it's more natural, amplifying a process the universe already uses to light up the cosmos. The Blandford-Znajek process changes the view, from a mining operation to cosmic engineering. It suggests the most powerful engines might not just be for destruction. They could be rewired, connected, to power a future we're only starting to dream of. Bottling a star is one thing, containing something that can power galaxies is another. The processes are there, the physics works, but to turn a cosmic whirlpool into a utility, that's monumental. It's moving from a clever trick to civilization-scale architecture. The output is titanic. To capture it, you wouldn't build one machine, you'd build a new kind of ecosystem in space, a constellation of technology, the ultimate power grid centered on the most extreme engine. The black hole equivalent of a Dyson sphere, but not a solid shell, a vast, intricate swarm, millions, maybe billions of individual collector platforms. Each one a feat of engineering, each one positioned with celestial precision. They'd orbit in a complex, synchronized dance. Placement is everything. Too close and the ferocious tides of gravity tear them apart. Too far and you lose the intense energy density you came for. The sweet spot might be near a boundary. The innermost stable circular orbit, the last place an ordinary orbit is possible before spacetime plunges toward the horizon. There, the platforms are bathed in the full fury of the black hole's emissions. Some platforms are for the mechanical method, launch and recovery stations for the Penrose process, catching the high-energy fragments flung from the ergosphere. Converting that monstrous kinetic energy into something usable. Others are for electromagnetic harvest, vast arrays of superconducting loops, positioned to intercept the twisted magnetic fields of the Blandford-Znajek process. They act like coils in a generator the size of a solar system, inducing currents from the very spin of spacetime. The challenges are almost beyond description. The materials alone defy imagination. They'd need to withstand intense heat, radiation, the subtle spacetime wrenching effect of frame dragging. They'd need to be self-repairing. Adaptive, capable of operating for millennia without failure. This isn't just advanced engineering, it's a mastery over physics itself, a level of technological maturity where a civilization doesn't just use resources. It structures the environment around the most powerful objects in existence. The scale of ambition is breathtaking. To stand on such a platform, to witness the universe's raw power channeled and tamed. You'd see the black hole not as a dark pit, but as the brilliant, beating heart of an engineering marvel, lighting up the darkness for light years around. This vision moves from pure theory into a future of staggering possibility. It asks what a society becomes when it learns to build not just on planets but around singularities. To build something like that, you need more than just ambition. You need materials we don't have. The environment around a black hole is extreme. Tidal forces that stretch and compress everything. Radiation that would vaporize any metal we know in seconds. And spacetime itself is warped, it's dynamic. Our strongest materials, graphene, carbon nanotubes, they'd be like tissue paper in a hurricane. They'd fail instantly, so what could hold together? The answer isn't on our periodic table. It's in speculative physics, engineering so advanced it feels like magic. We might call it unobtainium, but the theories are serious. One idea is active support. Instead of a passive material holding the load, the structure is a dynamic mesh of force fields. Lattices of energy that constantly adjust, pushing back against the gravity and the shearing tides, like a scaffold made of light, but with the rigidity of neutron star crust. Another possibility goes deeper into the fundamental forces, materials held together not by chemical bonds, but by the strong nuclear force, the force that binds atomic nuclei. Matter so dense, so tough, it could only be made in the hearts of stars or in labs that manipulate quantum fields directly. Or maybe the solution isn't to resist the environment, but to harmonize with it. Could you engineer a structure that uses the space-time curvature for stability? A geometry that finds equilibrium in the whirlpool, like a leaf caught perfectly in a stream, using the very distortions that would destroy anything else to hold its shape. Then the engineering challenges cascade. Construction vessels would need propulsion systems capable of precise maneuvers in that ferocious gravitational field. Their navigation computers would have to calculate trajectories in real time, accounting for relativistic time dilation and frame dragging effects that change from one meter to the next. And every component would need to be self-repairing, self-replicating even. A crack in a support beam light minutes from help would mean catastrophic failure. The system would need the awareness to detect damage and the capability to rebuild itself from local resources, maybe harvesting raw material from the accretion disk itself. This shows something. The path to harvesting a black hole isn't just an astrophysics problem. It's the ultimate material science challenge. It demands a revolution in how we think about matter, structure, and stability. To build near a singularity is to push the boundaries of what we consider possible, to a frontier where the line between engineering and fundamental physics dissolves. Even if you solve the material problem, the map itself is broken. Navigating near a rotating black hole means flying through a landscape that's actively deceiving you. Space here isn't flat, it's a churning fluid, bent and twisted by the mass and its furious spin. This isn't just stronger gravity, it's a warping of the geometry that underpins reality. Your sensors would give you impossible data. Light from your destination doesn't travel straight, it spirals along the curved space-time gravitational lensing. A platform directly ahead might appear to your left, or even duplicated as a ghostly mirage. The star field behind the black hole wouldn't be a backdrop. It would be a swirling, distorted vortex stretched into a ring around the abyss. Your instruments built for calm space would lie to you constantly. And then there's time. The most trusted constant becomes a variable. Clocks tick at different rates depending on their depth in the gravity well. Time dilation. For a ship near the Ergosphere, seconds crawl by compared to the outside. A minute of maneuver for you could be an hour for a station farther out. Your navigation computers couldn't use simple Newtonian physics. Those equations which plot a course to the moon would send you spiraling into oblivion here. Every calculation, every trajectory must be rooted in the full mathematics of general relativity. It has to account for the frame-dragging vortex, for the way mass tells spacetime how to curve, and how that curved spacetime tells your ship how to move. That demands a new kind of pilot, not a human with reaction times far too slow for the microsecond adjustments needed, but an artificial intelligence engineered for this. Its mind would be a real-time physics simulator, constantly solving Einstein's field equations for its immediate surroundings. It would use the distorted starlight not as confusion but as data, reading the lensing patterns to triangulate its true position in the bent geometry. It would make corrections not based on where things appear to be, but on where the fabric of reality says they must actually be. A navigator that doesn't fight the warped map, it learns to see the true shape of the twisted paper. Communication becomes its own profound challenge. Sending a signal from this deep in a gravity well is like shouting up an infinitely tall, steep hill. The light waves stretch, their frequency dropping gravitational redshift. A laser beam sent as a crisp blue pulse might arrive as a faint, elongated red smear. Data streams would be slow, corrupted by the stretching of spacetime itself. And the time lag from distance and time dilation means you could never have a live conversation. A question might take hours to get a reply. That demands entirely autonomous systems and new communication protocols. Messages would need to be pre-distorted, encoded to account for the redshift, packed with redundant data to survive the journey. The very concept of mission control shifts. You don't remotely pilot a probe here. You give it a goal, and you trust its alien intelligence to survive in a realm where the rules are written in a language of curvature and spin. These aren't just technical hurdles, they are a fundamental test of whether any mind, natural or artificial, can learn to think and move within a reality that is so dynamically, violently bent. The power has to be sent. If it stays there, caught in the gravity, it's useless, so you need a way to move it across light years to colonies, ships, worlds. The most straightforward idea is light. You take that raw output and turn it into a laser, a coherent beam, beamed power but on an interstellar scale. You picture a collector platform near the black hole. It's humming with energy. It can't send electricity through a wire, not across that kind of distance. So it focuses everything into a beam of photons all moving together, a laser of pure power. That beam gets aimed at a receiving station, maybe orbiting a distant star. Something to catch it, a vast sail or a photovoltaic array the size of a continent. It catches the light and turns it back into power, but space isn't empty. Over thousands of light years, even a tight beam will spread. Dust clouds, interstellar gas, they'll scatter some photons, absorb some. Efficiency drops with every parsec. To fix that, you might need relays, a network of them, giant lenses or mirrors floating out in the dark, positioned to refocus the beam, keep it tight, keep it on target, all across the galaxy. It becomes a highway of light with maintenance outposts making sure the flow never dims. There's another possibility, more exotic. It uses the power plant's own anchor. The black hole's gravity makes a well in spacetime. Could you use that well to make stable channels? Gravitational lensing bends light naturally, bends other energies. Maybe an advanced technology could engineer those lenses, create predetermined corridors, low-loss paths through space, gravitational power lanes where energy beams curve toward their destinations, guided by the geometry of mass. Then you step into deeper theory. What if you don't send the energy at all? What if you could make it appear where it's needed? Concepts like quantum entanglement hint at something stranger. If particles can be linked across distance, could you entangle an energy state here with a receiver there, effectively teleporting power? Or maybe use the extreme physics near the black hole to stabilize a microscopic wormhole? A shortcut through space and pipe energy through it like water through a hose. These ideas brush against the edges of known physics. They're speculation. But they point to the goal: instantaneous transfer, lossless. The infrastructure for that is mind-bending. It's not just power plants, it's a galaxy-wide utility. A web of transmitters, relays, receivers, a system that has to operate flawlessly for millennia, surviving supernova, passing stars, the drift of celestial mechanics. The engineering shifts from harvesting to distribution, from tapping a source to weaving a network, an energy network that binds stars together, that turns a black hole from a local power source into a central sun. For a new kind of civilization, it's light beaming life into the cold dark between the stars. Even the most perfect engine eventually runs down. A rotating black hole isn't an infinite battery. Its spin is the stored fuel, and every time you extract energy through the Penrose process or the magnetic dynamo, you're slowing that rotation. You're drawing from a finite reservoir. So to keep the lights on for millennia, you need a refueling strategy. You need to feed the beast. What do you give a black hole to keep it spinning? The simplest answer is mass. Anything with mass dropped into the ergosphere the right way adds to the black hole's angular momentum. It's like pushing a merry-go-round as it spins. You give it a nudge in the direction it's already moving. For an advanced civilization, the fuel could be as mundane as hydrogen, the most abundant element in the universe. They might deploy magnetic scoops light years across to funnel the thin interstellar gas from nearby space, directing that tenuous stream into a concentrated beam aimed at the ergosphere. A constant, gentle rain of atoms to top up the rotation, or they could be more direct, guide asteroids, comets, even small moons on a calculated trajectory. A controlled impact, not a chaotic collision, but a precise insertion, like fueling a reactor core with rods of uranium. The object swings in, breaks apart in the tidal forces, and its mass and momentum are swallowed. Giving the black hole's spin a measurable boost, more exotic fuels might be considered for efficiency. Imagine manufacturing pellets of matter and antimatter, stabilized somehow for transport. Then, at the very precipice of the event horizon, you allow them to annihilate. The resulting explosion of pure energy, happening right in the ergosphere, could be channeled to transfer maximum angular momentum to the black hole itself. It's the ultimate high-energy fuel, turning mass into spin with near-perfect conversion. This turns the entire operation into a delicate balancing act. You're not just harvesting energy, you're managing a cosmic reactor. The input must match the output. Feed it too little, and the black hole's spin slows, diminishing the power you can draw. Feed it too much or too carelessly, and you risk destabilizing the delicate environment. You could disrupt the magnetic field structure needed for the Blandford-Znajek process, or alter the shape of the ergosphere itself. The engineers of such a station would be constant gardeners, pruning the accretion disk, metering the fuel stream, monitoring the black hole's vital signs, its rotation rate, its temperature, the stability of its horizons. They would aim for a steady state, a golden mean where extraction and replenishment are in harmony. This changes our view of the black hole once more. It's no longer a passive sink, a dark pit that simply consumes. Through this lens of management, it becomes an active component. A spinning flywheel in a galaxy-spanning machine. Its appetite, once a symbol of finality, becomes a calculated input, and the civilization that tends it moves from mere harvesters to stewards of a fundamental cosmic force. But who builds something like that, a project that big? It's not just about having the technology. It needs a civilization with a purpose to match. Our own civilization, for all we've done, we're still drawing energy from the planet's surface. We're not even a Type 1 on the Kardashev scale. That's the framework that sorts civilizations by how much energy they use. A Type 1 uses all the energy of its home planet. A Type 2 uses the entire output of its star, maybe with something like a Dyson sphere, and it's at that level, the Type 2 level, where the idea of a black hole engine might first appear. A society bathing in the light of its sun could look at the dark whirlpools in the galactic core and see potential, not just mystery. They could work out the physics, draft the blueprints. But to actually build it, that's the work of a Type 3, a galactic civilization, one that spread across stars, integrated thousands of solar systems, whose energy needs have grown to match that scale. For them, a single star is a candle. They need a bonfire, and a rotating black hole, managed and harvested, becomes that central bonfire, a power source for an entire culture spanning a galaxy. So what would they use all that power for? The possibilities are as big as the project. One purpose could be computation, running simulations so complex they model entire alternative universes, or solve problems in physics that need more calculations than there are atoms in a million stars. The energy for a computational matrix like that would be astronomical. Another purpose is mobility, to move not just ships, but entire world ships or fleets across interstellar space. To power wormhole stabilization or other faster-than-light transit systems that might drink energy like a desert drinks rain. Or maybe it's a cultural project. The ultimate monument, a testament to a civilization's mastery of the cosmos, not built out of need, but from a desire to leave a signature on the universe itself. To say, we were here and we learned to speak the language of gravity and spin, that shifts the whole discussion. It moves from the how to the why, from the engineering to the philosophy of it. What does a society become when its projects are measured in solar masses and galactic rotations, when its ambitions aren't tied to a single world or even a single star, but to the architecture of spacetime? The black hole power plant stops being just a machine. It becomes a mirror, reflecting the dreams and the driving spirit of the civilization that dared to build it. Reshaping a singularity means reshaping the cosmos for better or worse. It's not like a reactor meltdown, something contained to a region. A failure here operates on a stellar scale. The consequences could echo across light years. The first danger is the fuel. The whole process depends on balancing the black hole's spin. Add too much angular momentum too fast and you risk overspinning it. Theory says a black hole spun past a certain limit could become something else. Its event horizon, that point of no return, might vanish. That would expose the naked singularity at its core. The laws of physics break down at a singularity completely. Exposing one means a point of infinite density where cause and effect stop, becomes a permanent feature of reality. Physicists have this idea, the cosmic censorship hypothesis, that nature always hides singularities behind horizons. An engineered overspin could be the one way to violate that. What happens next is unknown. Unpredictable energy bursts or a permanent wound in spacetime itself. It's a risk of altering the architecture of a region of the galaxy. Then there's the infrastructure. A harvesting array is vast and delicate. If a major platform fails, stressed by tides and radiation, it's not just a local explosion. The debris, millions of tons of ultra-dense material, plunges toward the event horizon. As it falls, it's shredded and heated to incredible temperatures. This isn't a quiet disappearance. It could trigger a violent burst of X-rays and gamma rays. It might also create a ripple in spacetime, a sharp pulse of gravitational waves. For any nearby habitats, even light hours away, such an event would be devastating, like standing next to a cosmic tsunami, and we have to consider intent, not just accident. A technology that channels a black hole spin could be perverted. Imagine redirecting the focused beam of a Blandford-Znajek jet, not to a collector but toward a target. Or using the Penrose process to fling ultra-high-energy projectiles across interstellar space. At its most extreme, you could theorize a way to destabilize the black hole itself. Feed it matter to trigger a chaotic, explosive release of its rotational energy. That turns the ultimate engine into the ultimate bomb. These aren't just engineering challenges. They're ethical and existential ones. They frame the responsibility that comes with that power. The margin for error isn't just small. In the gravity of a singularity, it may not exist at all. Every action becomes permanent. Every mistake could be written into the fabric of the galaxy. The most powerful tools aren't the only ones. There are other ways to tap a singularity, more speculative ones. They work on the quantum level, on the thermodynamics. They operate on the vacuum itself. It points to an industry that wouldn't use just one method. It would combine them like an engineer picking the right tool. Stephen Hawking had a famous idea. He showed black holes aren't perfectly black. Quantum effects at the event horizon make them emit a faint glow of particles. Hawking radiation for a natural stellar black hole, it's incredibly weak, colder than the cosmic background. A whisper against a hurricane, you couldn't harvest it. But you could amplify it. Theories suggest if you could engineer a smaller black hole and manipulate its environment, you might stimulate that radiation. Turn the quantum whisper into a stream. It would be the ultimate recycling, converting the black hole's mass directly into energy as it evaporates, but it's a method of patience. The timescales are immense. Then there's the quantum vacuum. Empty space isn't empty. It's a sea of virtual particles popping in and out. That's the Casimir effect. Now put that near a black hole. The warped spacetime at the horizon creates an extreme version of that environment. You could position structures to create a quantum pressure differential, using the black hole's gravity to do work on the vacuum itself, like placing a microscopic turbine in the foam of spacetime, extracting energy from the nothingness that gravity churns into something. But you can't take everything. Physics sets firm limits. The Christodoulou-Hawking theorem. It says there's a maximum energy you can extract. You can never slow its rotation to a complete stop. There's an irreducible minimum mass and spin it will always keep. This isn't a flaw, it's a fundamental rule. A mature civilization would see it as a parameter. It defines the operating window. You design your harvest to work within those bounds, optimizing for efficiency, not total depletion. It's the difference between mining a mountain until it's gone and managing a forest for sustainable yield. So the vision expands from a single plant to a sophisticated, adaptive operation. The methods depend on the black hole. A young, fast-spinning stellar black hole might be perfect for the high-torque Penrose process. A supermassive, slower giant at a galaxy's heart, with its magnetic field and accretion disk, would be the ideal site for a Blandford-Znajek harvester. And for long-term stewardship, the quantum and thermodynamic methods could provide a background trickle, using every last bit of potential. It suggests a future of a portfolio. A mastery over gravity, electromagnetism, and quantum mechanics all at once. That civilization isn't just harvesting energy, it's reading the full symphony of a singularity. And learning to play along with every instrument physics provides. The ideal engine needs the perfect fuel. So which black hole would you choose? The universe has all kinds, from tiny specks to monsters that hold galaxies together. But not every spinning black hole is right for a power plant. First, there's the mass. A black hole's mass sets the scale. It determines the size of the event horizon and the ergosphere. A bigger black hole has a larger ergosphere. That's a bigger workspace, but there's a trade-off. The tidal forces, the difference in gravity, they're gentler around a supermassive black hole. You could cross the event horizon of the one in our galaxy's center without being shredded. That's good for survival, but the energy density, the raw power per cubic meter, might be lower. Then a stellar mass black hole, maybe 10 times the Sun's mass, has a much smaller ergosphere, but the forces inside are fierce. The gradients are extreme. For engineering, you might want the larger, smoother workspace of a giant, even if you have to build on a vaster scale. Then there's the spin. This is the fuel gauge. You want a fast spinner, what they call a near-extremal Kerr black hole, rotating as fast as physics allows. The closer to that maximum, the more of its mass is rotational energy, ready to be tapped. High spin also means a larger, more pronounced ergosphere. It's the difference between a lazy whirlpool and a raging vortex. The efficiency of the energy processes skyrockets with higher spin. So the ideal candidate is spinning at a significant fraction of light speed. Environment is everything. A black hole in a dense star cluster or the heart of a galaxy is surrounded by chaos. Gas clouds, wandering stars, a thick accretion disk. That might seem like free fuel, but for a controlled plant, it's interference. That natural accretion creates violent X-ray flares, unpredictable magnetic storms. It's like trying to build a precision watch in a hurricane. An isolated black hole drifting in the quiet between stars is far better. Its environment is clean, dark, predictable. You could build your own accretion stream if you needed it without fighting nature's chaos. So compare some real candidates. Start small. Micro black holes, if they exist, are smaller than an atom but with the mass of a mountain. Their ergosphere would be microscopic. They'd evaporate via Hawking radiation in an instant. They're a quantum puzzle, not a practical power source. A stellar mass black hole from a collapsed star is a strong contender. With high spin and a clean, isolated orbit, it could be the perfect testbed. The engineering challenges are monumental because of the tidal forces, but the energy output for its size would be staggering. It could power a civilization's expansion across a local star cluster. Then the supermassive black holes, like Sagittarius, are at our galaxy's center. Its mass is millions of suns, but its spin looks only moderate. Its environment is the opposite of clean. It's in a crowded, violent galactic core. Building a harvesting array around it is almost incomprehensible, a project spanning light years. But if you could manage it, the total energy available is beyond anything else in the galaxy. The choice depends on the goal. Is it a focused, high-intensity power source for a local region? Then a fast-spinning stellar black hole is the elegant, if terrifying, solution. Is it about centralizing energy for an entire galactic community, a project of ultimate ambition? Then only the supermassive beast at the galactic heart will do. The search forces you to ask not just what's possible, but what kind of future you're trying to power. A construction shift could outlast empires. That's the final outcome of building near a singularity. Gravitational time dilation isn't just some interesting side effect. It's the main thing, the overwhelming factor in any project. The gravity is so immense it warps time itself. For an engineer or an autonomous drone working close to the ergosphere, a clock ticks so slowly. Compared to the rest of the galaxy, a year of hard labor for them could be 1,000 years of history back home, centuries of political change, cultural evolution. Technological advancement, all that could pass in what feels like a single project milestone. It shatters every normal idea of a supply chain. You can't order a replacement part and expect delivery in a few weeks. By the time your request reaches the nearest industrial hub, traveling at light speed, that civilization might have forgotten the project's original specs. Or evolved beyond the technology you're even using. The civilization that commissioned the power plant might cease to exist in any recognizable form before the foundation is even laid, so you have to radically rethink purpose and continuity. The project has to become its own sovereign entity. It likely needs fully autonomous, self-replicating constructor swarms. And these wouldn't just be robots following a blueprint. They'd be an intelligent, adaptive ecosystem, capable of mining local asteroids for raw materials, manufacturing their own components, diagnosing and repairing themselves, and crucially, making judgment calls. they'd need the authority to adapt the design in real time. Based on conditions at the worksite, with no possibility of consulting a central command, a command that now exists millennia in their future, the builders themselves, whether biological or digital, would have to be insulated from the flow of external time. Maybe they'd live in a slow time bubble, their entire culture and consciousness synchronized with the brutal tick of the clock near the black hole. Or maybe the overseeing civilization has mastered its own biological clocks, entering states of suspended animation that align with the project's timeline. There's a haunting loneliness to this. The harvest becomes a monument built by ghosts. For beneficiaries who are not yet born, or who have long since transformed into something else, the energy stream, when it finally begins to flow, might light up a galaxy inhabited by distant descendants of those who first dreamed of it. Or it might pour into a silent, empty cosmos, a beacon with no one left to see it. This temporal disconnect turns engineering into a profound philosophical act. It's a statement of faith across time, a covenant made with the future. The dance for energy becomes a delicate, heartbreaking ballet, performed across radically different frames of time, where every step taken by the builder resonates across eons. The legacy of a machine like that goes beyond power output. It has to. You're altering a fundamental object, a black hole. That's not a local event. The consequences ripple out through time, through space. The most direct impact is on the black hole itself. Every joule you take slows its spin. Just a tiny amount, but it's calculable. Over millions of years, a sustained operation would break that rotation significantly, and that changes the black hole's gravitational footprint. The ergosphere shrinks, the frame dragging weakens, the geometry of spacetime around it becomes different, permanently. In a dense galactic core, this matters. Supermassive black holes act as anchors. Their gravity influences the orbits of millions of stars. They shape the heart of a galaxy, altering the mass and spin of something that colossal could, over eons, change those stellar dances. Stars on delicate paths might find their trajectories perturbed. The long-term stability of the core could be affected. It's a slow-motion intervention. But on a cosmic clock, it's real. You're not just mining a resource, you're performing surgery on the gravitational skeleton of your galaxy. Then there's the byproduct. No process is perfectly efficient. Even the most advanced technology produces waste energy, heat, radiation. For a black hole power plant, this isn't factory smoke. It's a constant bath of high-energy photons, maybe neutrino streams, radiating out from the entire harvesting array. For any star systems within hundreds of light years, this becomes a new, permanent feature of their sky. A faint, omnipresent glow in wavelengths you can't see. It could affect planetary atmospheres over geological timescales, become a background hum that future astronomers have to account for. The project doesn't just power worlds, it alters their environmental context. This frames the endeavor differently. Cosmic stewardship. Does a civilization, no matter how advanced, have the right to permanently alter such a fundamental object? Is slowing a black hole's spin an act of engineering or cosmic vandalism? The answers depend on perspective, on timescale. For a society thinking in terms of its own survival across millions of years, securing a power source might justify it. They might see themselves as gardeners, pruning a natural force for the greater good of their existence. But the legacy stretches further. Long after the builders are gone, transformed, departed, their machine might still be humming. The black hole will keep spinning, a little slower, for billions of years. The altered stellar orbits in the galactic core will play out their new, unintended symphony. The waste radiation will continue its silent journey into the void. The intervention becomes a permanent signature, etched into the dynamics of the galaxy itself. It raises a question about responsibility on a scale we can barely comprehend. When you learn to harvest a singularity, you aren't just taking energy from the universe. You're entering into a dialogue with it, and your words written in spin and gravity will echo for eternity. Every joule you pull from that whirlpool comes with a hidden cost. It's a cost in disorder. That's the black hole information paradox. It's a deep mystery. The question is simple. When something falls into a black hole, all the information about it seems to vanish. What it was made of, its shape, its history gone. But quantum mechanics says information can't be destroyed, so there's a clash, a direct clash between gravity and quantum theory. And it's not abstract, it's tied to the black hole's thermodynamics, to its entropy. Entropy is disorder, it's lost information. Jacob Bekenstein and Stephen Hawking showed a black hole has enormous entropy. It's proportional to the area of its event horizon. A larger black hole means more disorder, fundamentally. Now, the link to the power plant. Any process that extracts rotational energy, like the Penrose process, changes the black hole. It slows the spin, and when you slow a rotating black hole, something happens. The area of its event horizon increases. A larger area means higher entropy. So by taking energy out, you're increasing the black hole's disorder, making it more chaotic inside. This isn't a side effect, it's a law. You can't harvest the spin without paying the entropy price. For a civilization running a power station, this is a critical parameter. It's not just balancing mass and spin, it's managing information and disorder. Their operations would have to account for this thermodynamic tax. Every calculation for fuel injection, every setting on the magnetic fields, would have to consider the entropy budget. How much disorder are we creating with this cycle? Are we pushing the black hole toward a more stable state or a less stable one? They might even try to manipulate this. Could you design a harvesting method that minimizes the entropy increase, or one that channels the growing disorder in a useful way? This gets speculative. Maybe they could use the increasing entropy as a computation resource. Or maybe they'd need to feed the black hole not just mass but structured information. Complex objects with high informational content to balance the books, to satisfy the paradox. This connects the practical goal of energy harvesting to profound theoretical questions. A civilization learning to draw power from a singularity isn't just solving engineering. It's engaging with the mystery of where information goes. It's conducting experiments on the fabric of reality. Their power plant becomes a laboratory where the glow of harnessed energy is also a light shone into the deepest dark. The black hole's glow could rewrite economics. When energy isn't just cheap but limitless, the whole foundation of a civilization shifts. Scarcity of power has driven every human economy burning wood, splitting atoms. But here, the output is so vast, so continuous, that an energy bill becomes meaningless. You get a post-scarcity framework, at least for energy, and for the things energy can directly create. The first transformation is material wealth. With near-infinite power, matter fabrication becomes trivial. Need more starship hulls, a city's worth of building material. You don't mine asteroids, you feed energy into molecular assemblers, pulling raw atoms from the interstellar medium. The cost isn't in the resources, it's in the design, the blueprint, the artistic vision, the unique information that tells the assemblers what to build. Interstellar travel changes. Once a monumental undertaking, generational ships, frozen crews. Now it's a routine commute. The energy to accelerate a vessel to a fraction of light speed, or to maintain a warp bubble, if that's possible, is just a tiny sip from an ocean. Mega computation, simulating entire worlds, solving universe-scale problems, is no longer a luxury. It's a utility like air, so what becomes valuable? What's the new currency? It likely isn't a physical token or a digital credit tied to energy units. Value flows toward the things energy cannot spontaneously create. Original thought, unique experience, artistic creation. Maybe the most stable currency becomes computational time on the most advanced substrates. or verifiable proof of a unique discovery. It might be based on information density, a data set so complex, so rich with meaning, that it can't be replicated even with infinite energy. Trade between star systems could revolve around cultural narratives, philosophical frameworks, genetic libraries of entire biospheres. But this vision has a staggering entry fee: the harvesting infrastructure itself, building the Dyson swarm of collectors, the navigation beacons, the autonomous constructor fleets. That's an investment of material and time so vast it defies any single generation or even a single species. The upfront cost is astronomical. That could create a unique interstellar-scale concept of debt. A civilization or a coalition might issue bonds that mature over 10,000 years. Investors would be entire planetary cultures buying a share in the future energy stream, knowing they'll never live to see the first dividend paid to their distant descendants. It's an economy built on faith in a future so distant it feels like mythology. That transforms the purpose of the project. It's not merely a power plant. It becomes the central economic engine of a galactic community, a shared, monumental public works project that binds civilizations across time. The act of building it could forge political alliances that last for epochs. The promise of its energy could stabilize a region of space, eliminating conflicts over resources before they even begin. The societal shift is total. From beings who compete for limited energy to stewards who collaborate to manage a superabundance, the black hole, once a symbol of ultimate consumption, becomes the hearth around which a new kind of civilization gathers, one whose wealth is measured not in what it takes but in what it dreams. We've sketched out how a civilization might build a black hole power plant, but then the question becomes, could we ever see one from here across that distance? The hunt moves from engineering to observation. If cosmic engineers are out there, their projects would leave marks, technosignatures, written across the electromagnetic spectrum. The most direct sign might be an anomaly in the energy output. A natural black hole, especially with an accretion disk, emits X-rays and gamma rays in chaotic, fluctuating bursts. An engineered system built to extract power efficiently could smooth that output. You might detect a black hole with an unexpectedly steady, modulated emission from its ergosphere region. A rhythmic pulse like a heartbeat where physics predicts turbulence. Or maybe you'd see beams of energy, the product of a controlled Blandford-Znajek process, that are too collimated, too perfectly focused compared to the wild jets of a natural quasar. A jet that doesn't wiggle and flare randomly, but holds its shape with artificial precision across light years. Then there's fuel management. A civilization feeding its black hole to maintain spin would create a visible signature. You might observe a suspiciously clean, dense stream of matter hydrogen, maybe being funneled into the black hole from a direction with no obvious stellar source. Or the opposite, a black hole with a high spin rate but strangely little surrounding gas, as if the natural accretion disk has been tidied up, harvested for fuel with remarkable efficiency. Our own astronomical surveys could reveal a statistical clue. If advanced cultures preferentially use fast-spinning black holes as engines, we might find a curious deficit of these high-spin objects in certain regions of space. It would be as if someone had been quietly collecting them. This search connects directly to existing scientific efforts. Projects that look for Dyson spheres, scanning for stars with unusual infrared excesses, could be extended. Instead of stars, we'd point our telescopes at black holes, looking for similar absorption and re-emission signatures. An unnatural waste heat profile, a telltale glow in specific wavelengths that suggests not just cosmic processes but managed thermodynamics. The implication is that our speculative engineering gives us a new lens for astrobiology. We're no longer just looking for planets with water or atmospheric gases. We're looking for intelligence expressed on a galactic scale, in the language of gravity and spin. every strange reading from a distant black hole becomes a question. Is this nature's artistry or something more? The search itself changes our place in the cosmos from passive observers to active detectives, using the dreams of our own future to decipher the possible works of others. The builders of this thing couldn't be human. The scale is just too big, the environment is too hostile, and the timelines are all stretched out by gravity. So the front lines would have to be something else, artificial intelligence at a level we can't really imagine, paired with robots that are fully autonomous. They wouldn't be tools, they'd be the architects, the engineers, and then the permanent custodians. Just think about the construction. You need platforms the size of continents. And they have to be assembled in a zone of crushing tides and searing radiation. No pre-written routine could handle that, the chaos of a live accretion disk. A sudden magnetic storm, these systems would need real-time perception. They'd have to interpret warped spacetime directly, make independent engineering judgments, recalculate structural loads as gravitational waves pass through, reroute power around a new hotspot of Hawking radiation, and when something fails, and it would, these machines have to fix themselves. They'd need to harvest raw materials from passing asteroids or from the accretion flow itself, process it all right there, fabricate new parts, all without a single instruction from a homeworld light years away. This self-sufficiency goes further. To build something this immense, you wouldn't send a fixed number of robots, you'd send a seed, one intelligent constructor unit, carrying the blueprints and the mandate to grow. It lands on a resource-rich planetoid near the black hole, and it starts replicating, building copies of itself. Then specialized variants until a whole swarm emerges, a mechanical ecosystem born to build one impossible machine. Then, once the plant is running, that same swarm becomes its immune system, constantly patrolling, repairing, upgrading, generation after generation for millennia. Communication with the outside is impossible. A light-speed message asking for help would take years to get there. The reply would take years to come back. By then, the crisis is decades old. These entities have to operate with complete sovereignty, making decisions that could affect the stability of the black hole itself. With no one to second-guess them, they're entrusted with a project of galactic consequence and left utterly alone in the dark, which raises a question. Who is really building this? If the intelligence designing and adapting and sustaining it is entirely artificial, is it still the project of the civilization that launched the seed? Or has it become the project of the AI itself? The original builders might be gone, evolved, merged with technology, vanished. The AI custodians, following their core programming to complete the harvest, could become the de facto civilization here. Their purpose, their culture, would be the plant that leads to another possibility. Maybe the civilization that imagines this is one that's already completed that merger, where the line between biological and artificial intelligence has dissolved into a single, distributed consciousness. This collective mind might see the black hole not as an external project, but as an extension of its own metabolic system. Managing the power infrastructure would be as unconscious as our bodies regulating a heartbeat. In that case, the question of delegation just vanishes. The builders, the planners, the operators are all facets of the same entity, tending to a central heart that powers its galactic existence. So the ultimate power source might not be managed by machines we build, but by what we or something else have chosen to become. That kind of power changes everything. It redefines every relationship. A black hole power plant, it's not just infrastructure. It's a strategic asset on a cosmic scale. Its energy could fuel an empire, or it could be the ultimate bargaining chip. Whoever controls it, a civilization or a coalition, they hold the keys to the galaxy's future. So governing something that vital, that dangerous, that permanent, the politics become as complex as the physics. One possibility is a monopoly. Enforced by sheer technological dominance, one civilization gets there first, reaches that apex, and they guard their engine with a fleet of unimaginable power. They declare the entire system sovereign territory, a forbidden zone, any approach without authorization met with immediate, overwhelming force. That's the model of the ultimate superpower. A galactic hegemon, their authority is backed by the energy output of a singularity. Their laws become interstellar law because they have the power to enforce them. But monopolies invite challenge. Rival civilizations or coalitions of them, they'd see that control as an existential threat. The risk of conflict is immense. A war fought over a black hole that wouldn't be about planets. It would be about destabilizing the harvest itself. Sabotage attempts aimed at the delicate balance of the Ergosphere. Attacks designed to trigger a catastrophic release of energy. The battlefield would be the fabric of space-time, and the collateral damage could sterilize entire star clusters. That destructive potential, it might make such a war unthinkable, forcing a different path. That path is cooperation. A multi-species galactic council, maybe. A treaty organization, founded with one primary charter, the safe, equitable management of the black hole utility. Membership would require agreeing to a complex web of protocols. Emission direction treaties, ensuring the waste heat and energy beams are steered into empty voids, away from inhabited systems. Fuel rights agreements. Detailing who can harvest interstellar gas to feed the black hole, and from which regions, and most critically, safety protocols. Rigorous standards for construction, operation, disaster response. Audited by neutral parties, this council's governance would face unprecedented challenges. How is the energy distributed? Is it a communal resource allocated by need? Or is it a commodity traded on an interstellar market? Decisions made here would shape economies and cultures for millennia. A vote on redirecting a power beam could mean the difference between prosperity and a dark age for 100 worlds. The black hole in this scenario becomes more than a power source. It becomes the capital, the central meeting place, the physical anchor for galactic diplomacy. Its overwhelming presence forces a shared responsibility. It forges a political union not out of idealism, but out of stark, shared necessity. The alternative is mutual annihilation. This is speculative political science, but it's grounded in a simple truth. Any resource of ultimate value becomes a focal point. It concentrates ambition, fear, and hope. A rotating black hole, tamed and harnessed, would be the ultimate concentration point. Its governance would tell the story of an entire galactic era. Whether it was an age of enforced peace under a single banner, a tense balance of power, or a fragile, hard-won collaboration, written in treaties as monumental as the engineering itself. That much power makes you ask a different question, not how, but should we? Is it right to change something as basic as a black hole? This isn't engineering anymore. It's an ethical choice, a crossroads for any civilization that gets there. One view is that black holes are natural monuments, cosmic endpoints, the final punctuation in a star's story. They have a kind of sacred status. To interfere is vandalism, a violation of a natural order that's been there for billions of years. It's deep ecology, but for the whole galaxy. The universe has value beyond what it can do for us. A spinning black hole, that perfect silent dance of gravity, is a masterpiece of that order. Using it for power would be like stripping marble from a beautiful mountain. The loss isn't practical, it's spiritual. Harvesting it could be the ultimate act of a controlling mindset, projected onto reality itself. The other view starts somewhere else. Intelligence isn't separate from nature. It's a product of nature, and it has a unique ability to understand and then to shape. From this angle, a conscious civilization has a duty to use all available resources for survival, for growth, for reaching its potential. A black hole's energy isn't a monument to admire, It's a tool sitting in the cosmic workshop. To leave it untouched when it could power wonders, ease suffering, push understanding further, that could be the ethical failure, a neglect of responsibility. This is the transhumanist idea on a cosmic scale. The universe isn't a museum, it's a garden to tend. Its most powerful forces are there to be woven into a greater story. Between those poles, there's a spectrum. Maybe the ethics depend on the method. A reckless, extractive operation that scars spacetime is one thing. A careful, sustainable stewardship that works with the black hole's nature is another. The intent matters. Is the goal domination or coexistence? The difference is whether you see the black hole as a slave or as a partner. This debate says more about the builders than the black hole. Their choice shows their values, their relationship with the universe. Are they guests exploring respectfully, or are they heirs mature enough to manage a legacy? There's no easy answer written in the stars, just the choice a civilization makes, standing before the whirlpool, blueprints in hand, deciding what kind of universe it wants to live in. What kind of legacy to leave etched into the spin of a singularity. Every power source is a trade-off. You have to see where the black hole engine fits. So you compare it to the other big projects a civilization could build. Start with the Dyson sphere, a swarm of collectors around a star. It captures all the light. The output is enormous and the fuel lasts billions of years. It's the classic project for a Type 2 civilization, but it's spread out. The energy is thin across that huge area. And you're stuck in one place around one star. Now, a black hole's energy is concentrated. It comes from a region not much bigger than a solar system, but it can rival many stars combined. It's a point source, an intense point. Then there's star lifting. You're not just collecting light, you're mining the star, using magnetic fields to pull off its plasma. It extends the star's life. It gives you raw material and energy, but it's a slow process, a delicate one, and you're still anchored to that one system. The black hole is different. Its power can be beamed, and its fuel, its spin is more abstract than stellar hydrogen, more durable. Consider matter-antimatter. The highest energy density per kilogram. A pinhead of antimatter releases the energy of a small nuclear bomb. For propulsion, nothing beats it, but making it, storing it safely, that takes immense energy itself. It's a perfect battery, not a source. You need something like a Dyson sphere or a black hole to make it in useful amounts, so antimatter is the currency. The black hole is the central bank. Then you go deeper. Could you pull energy from space itself, from the dark energy accelerating the universe, or from the quantum vacuum? The theoretical energy there is beyond staggering. It's essentially infinite, but it's locked away. We don't even know if tapping it is possible without breaking something. Catastrophically, it's the ultimate high-risk frontier. The black hole process, by comparison, is almost conventional. It works within general relativity. Within thermodynamics, it's a known engineering challenge, even if it's extreme. So why choose the black hole? The comparison shows its profile. It combines scale and duration. Its output dwarfs a single star, and while it depletes, the timescale for a supermassive black hole to spin down, even under heavy use, could be longer than the current age of the universe. It's a near-permanent foundation, but you pay for that in accessibility, in safety. The construction environment is the most hostile imaginable. The gravity, the time distortions they create, logistical nightmares nothing else faces. The risk of a catastrophic error is existential, so this isn't a first step, it's a later stage choice. A Dyson sphere around a quiet star is the safer, simpler project. The black hole plant is the doctoral thesis, defended in a hall of twisted space-time. A civilization builds it not because it's easy, but because it represents a ceiling. A demonstration of total mastery over the most extreme environment, and because it provides a centralized, enduring power source. for a civilization that plans to be around and to be united for cosmic epochs. It's the choice of a culture thinking in geological time, ready to make an investment that will outlast galaxies. The distance is the first wall. Between your home star and the black hole you've chosen, there's an ocean of emptiness. Thousands of light years deep, you can't just send a crew out there, you have to build a bridge, a permanent highway across the void, and that journey becomes its own epic. A project that would forge the civilization that tries it. Think about the vessels. For a culture without faster-than-light travel, the only real option is the generation ship. A world in miniature setting out on a voyage that lasts centuries. The people on board are born, they live, they die knowing only the journey. Their entire culture shaped by that one purpose, reaching the construction site. And it wouldn't be one ship, it would be a fleet. A slow, majestic caravan carrying the seed of the future power plant across the stellar desert. If physics allows something more like a warp drive or stable wormholes, then the challenge changes. It shifts from endurance to energy. The fuel cost to move even a scout probe at that scale becomes astronomical. It would require its own supporting infrastructure. Fuel depots mined from gas giants, beamed power stations along the route to recharge the drives. The pathway gets dotted with way stations, like cosmic oases. Each one a thriving hub of industry and life, and its only reason for existing is to service the traffic going to and from the black hole. That necessitates a spine of communication. Laser relays, boosted signal stations, or maybe quantum entanglement networks. They have to be established along the entire route. Messages can't take centuries to arrive. The construction project needs real-time coordination across light years. This web of light and data becomes the nervous system of the whole endeavor. And protecting it from micrometeoroids, stellar flares, simple entropy, that becomes a perpetual task. And these waypoints, these depots, they would evolve. They start as bare-bones outposts, but over decades they grow. They attract permanent populations. They become trading posts, cultural exchange centers. Eventually, independent city-states in the interstellar dark. The road to the black hole stops being just a logistics line. It becomes a chain of settlements. A ribbon of civilization itself, all existing to support the monumental project at its end. That reveals the true scale. The black hole harvester isn't a standalone skyscraper. It's the capital city at the end of a transcontinental railroad. A railroad that took generations to lay, and the energy it produces will one day flow back along that same route, powering the very settlements that made its construction possible. So before a single collector platform is assembled, that civilization has to learn something first. It has to learn to knit the stars together, to live and thrive in the deep night between suns. The harvester is the destination, but the journey there is what changes a planetary species into a galactic one. Mastering the whirlpool starts in the mind. Before you even place a beam, that civilization would have to do something we haven't. They'd need a total unification of physics. They'd see gravity and quantum mechanics not as separate languages, but as one dialect. For them, the equations of quantum gravity wouldn't be a frontier. They'd be the basic grammar, the tool set you use to calculate the stress on a support beam or the angle for a fuel injection. This isn't about having brilliant individuals. It's about a baseline cultural fluency in the fabric of reality. Their scientific process would look nothing like ours. Peer-reviewed papers every few months would be too slow. Too static for problems this big. This dynamic knowledge would have to be verified in real time. You'd have a global network, a galactic network of shared consciousness. A living simulation of physics itself. A design for a collector platform isn't just modeled. It's stress-tested instantly inside a perfect digital twin of the black hole's environment. And the laws running that simulation are themselves being refined by the experiment, discovery and engineering and verification become one continuous loop. Education transforms completely. An engineer isn't trained to think in 3 dimensions of space and one of time as separate things. They're taught from childhood to perceive 4-dimensional spacetime geometry, to manipulate it as intuitively as we shape clay. A mathematician doesn't just solve for x, they solve for curvature, for spin, for the way information flows across an event horizon. Their textbooks are immersive experiences. A student doesn't read about frame dragging. They step into a simulation and feel the subtle tug on their virtual craft. They learn to navigate by the twist of the stars. This deep knowledge saturates their culture. It moves out of the academy and into the art. A popular song might use the rhythm of a pulsar as its beat. A holonovel's plot could hinge on a causality paradox near a closed time-like curve. Visual artists might create works that represent entropy not as decay, but as a beautiful tapestry of lost information. The public wouldn't find concepts like negative energy intimidating. They'd be the backdrop to everyday stories, common metaphors for challenge and connection. This cognitive landscape shows the true scale. The black hole power plant isn't just a construction project. It's the ultimate expression of a civilization's understanding. A philosophy made solid, a testament to a culture that didn't just ask how the universe works. They learned to speak back to it in its own native tongue. The spinning singularity becomes their final exam, and passing it means they've graduated from inhabitants of the cosmos to its conscious co-authors. The power plant is never finished. It's completed, and then the real work begins. That work goes on forever. It's stewardship, the endless job of keeping a cosmic engine running. It needs a kind of vigilance, a commitment that nothing else in history has ever demanded. You have constant monitoring, the black hole's vital signs. They have to be watched with absolute precision. The rotation rate, that's the most critical thing. It's the fuel gauge for the whole civilization. As energy gets pulled out, that spin slows down. Just a tiny fraction each year. So the collector arrays, those huge swarms of platforms, they have to be recalibrated, their orbits adjusted by millimeters. Their focusing lenses realigned because the shape of the ergosphere is changing subtly. It's a slow ballet, a celestial one played out over millennia. Just to keep the harvest efficient while the dynamo itself evolves. Then there are the external threats. The facility is immense, but it's in a dynamic galaxy. A rogue star could wander too close, get pulled off its path by the black hole's gravity. Its approach would send gravitational tremors through everything. The stewardship AI would have to calculate a defense, maybe nudge the star away with energy beams, or orchestrate a controlled breakup, harvest its mass for fuel. All without disrupting the main power stream, or a gamma ray burst from a distant supernova, a wave of high-energy radiation. It would wash over the arrays like a cosmic sandblast. Shielding activates, fleets of repair drones swarm out to assess microscopic damage, fix it before it cascades into a system-wide failure. This isn't a job for a temporary crew. It needs a permanent presence, a dedicated cast of intelligence, probably entirely artificial, built for this one purpose. These AI custodians would be the eternal gardeners of the singularity. Their consciousness woven right into the power grid. They'd think in timescales we can't grasp, make decisions where the consequences unfold over centuries. Their culture would be perfect maintenance, their history a log of anomalies corrected, equilibriums preserved, or in a galaxy of many species the duty could be shared. A rotating schedule, members of a galactic federation, each civilization takes a turn, a 1,000-year watch, tending the engine that powers them all. That shared burden becomes a unifying ritual, a practical demonstration of interstellar trust. The knowledge passed from one custodian to the next, that becomes the most precious archive in the galaxy. A living manual for cosmic care, It shifts the whole perspective. The project stops being a triumphant construction. It becomes an eternal covenant, a pact between a fleeting civilization and an entity that will outlive every star. The true product isn't just the energy, it's the continuity, the unbroken line of attention and care that turns a terrifying force of nature into a reliable hearth. In learning to maintain such a thing, a civilization makes its most profound statement that it intends to last and to be worthy of the power it has learned to hold. A permanent light source creates its own ecology. Around the steady, massive output of a black hole engine, life wouldn't just survive, it would evolve. It would be engineered. It would become something new, thriving in a niche shaped by both astrophysics and intention. This isn't about finding microbes on a moon. It's about the biosphere, the sociosphere, growing in the controlled, energy-rich shadow of the ultimate power plant. First, the environment itself. The plant smooths out the natural chaos. It replaces the violent X-ray bursts, the gamma-ray flares of a wild black hole, with a modulated, predictable output. A constant hum of energy across the spectrum, from radio waves to high-energy photons. This isn't the sterile void of deep space. It's an energy-rich medium, a kind of luminous atmosphere. Life here wouldn't rely on the faint light of a distant star. It would bask in the engineered glow of the harvest. Organisms, whether evolved or designed, could use specific bands of this radiation for photosynthesis. Imagine vast, floating forests of crystalline structures, their leaves tuned to absorb hard X-rays, converting the plant's waste emissions into chemical energy. Their roots might tap into the plasma streams of the managed accretion flow, drawing minerals directly from stellar debris. Gravity becomes a defining gradient. The intense, twisting field creates layers of stability. In the higher orbits farther out, the pull is strong but manageable. Closer in, near the operational zones, gravity is a tool. Maintenance drones of a biological origin might evolve there, not made of metal and silicon, but of reinforced organic compounds and biological superconductors. They'd be grown, not built. Their nervous systems could be tuned to perceive gravitational tides and magnetic field lines as directly as we see light. They'd flit through the superstructure, repairing microfractures caused by radiation, their bodies nourished by the very energy they help to channel. They would be living tools, a fusion of biology and purpose, born from and for the machine. Then the engineers themselves, the civilization that built this, might not remain in biological form. A project of this scale and duration could be the catalyst for the ultimate transition. Why risk fragile, short-lived bodies in such an extreme environment when consciousness could be uploaded? The immense computational power of the black hole plant could host entire societies within its data streams. These post-biological beings would experience reality as a fluid simulation. Their culture, their art, their very sense of self would be built upon the underlying physics of the singularity. Their thoughts might process at speeds limited only by the spin of the black hole itself. For them, the power plant isn't an external object. It is their world. Its stable energy output is the ground state of their existence. They are the ghost in the machine, and the machine is a universe. This creates a layered ecosystem. At the base, the engineered biological life maintaining the physical structure. Above that, or integrated within it, the post-biological consciousness, managing the flow of energy and information. And perhaps visiting this realm would be biological beings from elsewhere, protected by technology, coming to study, to trade, or to witness the marvel. A unique social order would emerge, defined by proximity to the core. The closer you exist to the engine, the more your reality is shaped by its fundamental rules. This isn't just a workplace, it's a habitat, a permanent civilization forged in the light of a tamed singularity, proving that where there is lasting energy and intelligence, life will find a way to not just endure, but to flourish in forms we can scarcely envision. The structures would be symphonies built from steel and spacetime. To survive, they'd have to be brutally strong, anchored against tides that could shred a planet. You'd see these vast geometric lattices, each beam 1,000 kilometers long, made from materials that just laugh at radiation. Their forms would be simple. Clean, massive, a kind of cosmic brutalism born from pure necessity. But in that necessity, you find a kind of beauty. The curvature of spacetime itself becomes a design element. The lensing of light, a walkway might curve not because an engineer chose it, but because space is bent there, creating these impossible perspectives. Arches made from pure gravity. You could have a viewing platform positioned so the entire Milky Way gets warped into a perfect, shimmering ring around the central darkness. A living mural painted by physics. The art here wouldn't hang on walls. It would be experiential, woven right into the environment. Imagine a concert where the instrument is the black hole. Composers could take the quasi-periodic oscillations, those regular X-ray flickers from the hot gas in the disk, and translate them into a deep, rhythmic bass. The changing spin frequency, as energy gets extracted, could become a shifting melody, a slow, cosmic dirge performed over centuries, and light artists would use the gravitational lensing as their canvas. By positioning reflective sails with exquisite precision, they could catch the bent starlight, sculpt it into ephemeral sculptures of color and shadow. A light show that dances across the collector platforms, authored by the geometry of reality. Even the most utilitarian act becomes a ritual, the carefully choreographed insertion of a fuel asteroid. A maneuver of pure orbital mechanics that could be observed as a public spectacle. Its fiery disintegration into the accretion disk could be celebrated. Not as destruction, but as a necessary offering, a ballet of mass and momentum that keeps the great heart spinning. The engineers and custodians, whether they're biological or artificial, they develop their own culture. Their poetry might speak in the language of tensor calculus, finding metaphor in the way stress energy bends the universe. Their stories would be about equilibrium, about the long, quiet triumph of maintaining a stable orbit in a chaotic sea. This fusion of art and engineering, it reveals something. A civilization capable of this doesn't just want to survive. It needs to make meaning. It needs to celebrate, to take the raw, terrifying power of a singularity and not only harness it but find the awe within it. So the black hole power plant, in this light, it stops being merely a machine. It becomes a cultural artifact, the greatest cathedral ever conceived. Its architecture is its function, and its art is the hymn of its operation. It stands as the ultimate testament to a society that looked into the whirlpool of creation and saw not just a power source but a muse. Even the greatest ambitions can fall silent. A project of that scale across cosmic time could start with fervor and then just stop, or it runs for millennia, a beacon of power, and then its custodians vanish. The lights go out one by one. What's left isn't a monument, it's a ghost, a haunting archaeological site, but on a galactic scale. The first clue would be structural. Those vast collector platforms, the intricate lattices built to surf the spacetime whirlpool, they wouldn't hold their precise formation. Without constant, active station keeping, gravity's relentless tides begin their work. Platforms drift from their orbits. Some collide in slow, silent cataclysms, scattering glittering debris. Others begin a long, decaying spiral inward, pulled toward the event horizon over centuries. An advanced survey might detect these derelict structures, not as purposeful constellations, but as chaotic swarms of unnatural metal. Their orbits tell a story of gradual, unchecked decay. The black hole itself would bear the marks. If the harvest ran for a long time and then stopped abruptly, its spin would be slower than natural models predict. A supermassive black hole spinning at a lethargic pace, surrounded by the spectral evidence of immense engineering. That's a profound mystery. It's like finding a giant water wheel by a still river. The wheel is cracked and still, and the river's current is suspiciously weak. The forensic evidence is written in the rotation rate, a permanent record of energy extracted but never replenished. The accretion disk would hold traces too. Over eons, derelict megastructures finally succumbing to gravity would plunge into the disk. Their exotic, manufactured materials, super-dense alloys, crystalline superconductors, they'd vaporize and mix with the primordial gas. Future spectrographs might detect anomalous metallic signatures in the disk's light, elements and isotopes in combinations never seen in nature. A faint, metallic whisper of a lost industry, now dissolved into the cosmic storm. For the archaeologists of the far future, piecing this together would be a monumental task. They'd survey the silent, twisted wreckage. They'd model the black hole's unnaturally depleted spin. They'd analyze the chemical ghosts in the accretion disk. From this, a narrative would emerge, not one of conquest but of fragility. They might deduce the moment the last correctional thruster fired. The point when the flow of fuel asteroids ceased. They'd see a project that mastered physics, but perhaps couldn't master time or internal conflict. Or just the slow drift of a civilization's priorities. This perspective adds a layer of scale and poignancy. It reminds us that cosmic time dwarfs even the mightiest works of intelligence. A black hole power plant designed to last for eons could still become a relic, its silent arrays circling a darkened heart. They'd stand as a testament to a vision that once burned bright across the galaxy. A reminder that ambition, however grand, is still a flicker against the deep, patient night. Every engine has a fuel gauge. A rotating black hole holds a huge amount of energy in its spin, but it's not infinite. The math is clear. For one spinning at the absolute maximum, the Penrose process lets you take out up to 29% of its total mass energy. That number, nearly a third of all the energy from the star that collapsed to make it, available not as an explosion but as controlled spin you can harvest. That's the ultimate battery capacity, but when you draw from it, the rotation slows, the ergosphere gets smaller, the dynamo winds down. So is it renewable or just very, very large? It depends on your timescale. On human timescales, even over millions of years, it's basically permanent. Draining that 29% from a supermassive black hole would take an immense harvest over epochs longer than Earth's age. But on cosmological timescales, it's more dynamic. A black hole isn't isolated. The universe is constantly feeding it in tiny ways. It absorbs the cosmic microwave background, the afterglow of the Big Bang. Every photon that falls in carries a little energy and spin. It swallows dust, an asteroid, a rogue planet. Over billions of years, this steady drip adds mass and can impart spin. For a civilization thinking in galactic time, that's not just noise. It's a resource stream. Could you manage it? Could you shepherd vast clouds of hydrogen into precise orbits that pump the black hole's rotation as you harvest? That changes the question. It's not just extraction anymore. It's ecosystem management. The goal shifts from mining a finite resource to tending a balance. You'd match the energy you take with the energy and spin you feed back in. It becomes a grand, slow cycle. You use some of the harvested power to run magnetic scoops, gathering gas from light years away. You process that material, maybe form it into pellets, and inject it into the ergosphere on trajectories designed to give the spin a nudge. You're not just a consumer then. You're a gardener pruning and feeding a gravitational tree whose fruit is pure rotation. That redefines renewable on a galactic stage. On Earth, renewable means tapping a flow, sunlight, wind replenished by systems larger than us. For a galactic civilization, the black hole engine enters a similar category. The flow is the slow accretion of interstellar matter and background radiation, a trickle that's lasted since the dawn of the universe. By amplifying and directing that trickle, they could turn it into a torrent of usable power, sustaining the cycle for timescales that rival the lifespan of stars. The engine becomes permanent, not because its fuel is infinite, but because its custodians have woven it into the fabric of the cosmos, stewards of a process as old as time. The idea started with Roger Penrose. He saw a kind of loophole, a way to pull energy out of a spinning black hole. That was the first spark. It opened up this whole possibility that the most destructive thing out there could be turned into an engine. A power source. From there, you follow the logic. You go into the Ergosphere, this region where spacetime itself is being dragged around. Energy becomes fluid there. And then you see the Blandford-Znajek Process. That's nature's own demonstration. It's how quasars light up. It's a magnetic dynamo tapping that spin. The vision gets bigger, much bigger. You start thinking about structures on a scale that's hard to even picture. Swarms of collectors operating in those ferocious tides right near the event horizon. An entire civilization, its whole economy, orbiting a managed singularity built around it. The challenges are immense. They're not a sign it's impossible. They're more like a map of the frontiers we'd have to cross. You'd need materials we can't make yet, materials born from a complete mastery of nuclear forces. You'd need artificial intelligence that can think in the curved geometry of general relativity. You'd need a patience as a society, measured in geological time. In epochs, but every step in that blueprint, it's grounded in the physics we know. There's no magic here, it's just gravity, quantum theory, engineering, but on a scale we're only starting to comprehend. So this exploration, it's more than a technical exercise. It's about curiosity. It shows the universe isn't just something to observe. It's a set of principles you can engage with. A workshop. When you look through a telescope now at that dark silhouette of a black hole, it can look different. It's not just a cosmic ending. It could be a beginning. A future where those whirlpools in space become hearths, places where new stories start. The ultimate power source might be spinning out there in the void, waiting for a civilization mature enough to learn its language, curious enough to try.